Okay, after working with the idea of a tangent line and after working with the idea of instantaneous velocities and instantaneous rates of change, we've certainly seen that there are certain similarities in all those definitions, and we're going to use these definitions to formalize what a derivative actually is. After what we've done in the previous presentation, this one, at least in terms of concepts, should not have any kinds of surprises here. So, how do we define derivatives? Well, we've seen in the previous presentation that these average rates that we talked about, slopes of secant lines, average rates of change, average velocities, were always quotients of differences. And instantaneous rates, instantaneous rate of change, instantaneous velocity, as well as the slope of the tangent line, those were limits of these difference quotients. Well, if we formalize that now, we will be able to separate computation from interpretation, which is nice. And that can help when you've got lengthy computations, because in a lengthy problem you don't want to sit there and try to visualize every single step. One of the purposes of computations is to simplify things and make it just computable. On the other hand, because derivatives can be viewed as velocities or slopes, that can help us interpret and visualize computations, and that too can help with lengthy computations, because that at the end will allow us to interpret the result and determine whether the result is sensible. And we will see that most definitely when we talk about tangent lines. Basically, the important thing here is to balance the computational structure, the structure of a problem, with the concepts themselves. If you try to put a concept into every step you're doing, you're probably going to drive yourself crazy. But if you try to take all the concepts out and just talk about computations, well, then the computations are basically useless because you cannot interpret the results. So balancing that out, and for every individual that balance will be struck in a different place, but balancing that out is what's going to make you a more successful professional than if you're working mostly on one side or mostly on the other side. So let's take a look at the definition here, and it's not surprising at all. If f is a function, then we're going to look at a point x0, so that a small open interval from x0 minus delta to x0 plus delta is contained in the domain of f. We remember that from talking about limits. We need a little bit of wiggle room to the left and to the right of the point. Then we define the derivative of the function at x0 to be the limit of difference quotients. The difference quotients are the average rates of change, f of x minus f of x0 divided by x minus x0. We take the limit as x goes to x0, and we call that thing the derivative, which is also denoted by f prime. That would mean here that here is a point, and if we are looking at an average rate of change from here to here, say, well, then of course that average rate of change just gives us a secant line. But as if we keep x0 at 1, if we now move this x closer to 1, we can see that these average rates of change, these slopes of secant lines, get closer and closer to the slope of a tangent line that we may be after here. And we can also see, that as our x is really close to the x0, the secant lines and the tangent lines are almost indistinguishable, and that's of course the starting point for numerical analysis, and that is something that we'd get to briefly later in this course, and that you will also see in your professional mathematics or engineering life, because a lot of good work is done numerically these days. Alright, so if this limit does not exist, then we will say that the derivative is undefined. And if the limit exists, we will call the function differentiable at the point x0. And the notation for the derivative is, we can denote it by f prime of x0. We can also denote it d dx f of x0, basically small difference in f divided by small difference in x, which is what this difference quotient does. That's also sometimes written df dx, and these things are also called Leibniz differentials, because Leibniz actually breathed some meaning into the differential difference in f and the differential difference in x. That is formally very hard to explain, but basically physicists and engineers often just look at a small difference in x, small difference in f, work with them like deltas, and don't worry too much about the limits. And that is something that mathematicians sometimes cringe at, but there is a way to formalize differentials. It would require a graduate level logic course and then a lot of model theory to get there. Plus, it doesn't connect to numerical analysis that much, which is really why the concept of the limit, which was also invented earlier, or put on a correct formal footing earlier than these differentials, which were only put on a correct formal footing in the 1960s. That is why we use limits typically. Okay, sometimes it's also just called df, derivative of f. And if the function y depends on time, then the derivative with respect to t is also denoted y dot, and that's Newton's notation. Newton just put a dot on top of things, called it a fluxion or something like that, and just kept on going. Leibniz at least tried to explain how he got what he got, and well, it took mathematicians a long time to figure out what these geniuses may have actually thought about as they were working with derivatives. Okay, proposition now. If you've got a function and a small interval from x0 minus delta to x0 plus delta is contained in the domain, then the derivative of f at x0 is also f prime of x0 being the limit as h goes to 0 of f of x0 plus h minus f of x0 divided by h, if that limit exists. This is the difference quotient, first of all, that is equivalent to what we had on the previous panel, because we know that from the limits we can also always go with base point plus h and then let h go to 0 to compute the limit. This is also the difference quotient that I would recommend to use for computations of the derivative, because it's a whole lot easier to factor an h out of a numerator than it is to factor a b minus a out of the numerator. Okay, if this limit does not exist, then f is not differentiable at x0, similar to what we had in the definition. It's just a translation to a different kind of difference quotient. Okay, so now let's look at an example. We are interested in the slope of the tangent line to the function f of x equals root x at an arbitrary x this time around. In the previous presentation we looked at x equals 1 or something like that. No, we didn't look at this one at all. So we're going to look at an arbitrary x here. Well, f prime of x, you just have to plug it in, right? You take the limit as h goes to 0, function at x plus h, square root of x plus h, minus function at x, square root of x, divided by h. And as we've seen in the computations of limits, this kind of stuff, well, what do you do here? You can't factor anything out, but whenever you're dealing with differences or sums of roots, one thing to do is to rationalize. This time we rationalize the numerator, which may not be something that people have talked about in algebra class, and I apologize for this not highlighting too well. That's just something that my program doesn't quite do well. Rationalizing numerators is something that you certainly don't do in algebra class, but we're not looking for a formal way to present things here. We're looking for a way to cancel h. So we're multiplying with the conjugate root x plus h plus root x divided by root x plus h plus root x. And if we now multiply out the numerator will be x plus h minus x, which is just h. And we're not going to multiply out the denominator. So we get x plus h minus x. The denominator is just kept the same, and we still work with the limit as h goes to 0. And, well, then as we simplify the numerator, we see that the numerator is h. And here's where we didn't want to multiply out the denominator, because now, of course, we want to cancel the h's. Remember, that was the point all along. In some ways, it's oversimplifying the idea here, but the idea typically is to cancel the h in the denominator. Okay, so we cancel the h's. Now we let h go to 0. We end up with 1 over root x plus root x. And that's 1 over 2 times root x, which is the derivative of the square root function. We can visualize that. Here's the square root function, and the derivative is 1 over 2 times root x, which means that at 1, the derivative, the slope of the tangent line, is about 1/2, and that feels about right. As the x increases, our slopes get less steep, which also makes sense. The square root function doesn't get steeper, it gets flatter, actually, as x gets large. And as x goes to 0, we get steeper slopes, and that is also reflected in here, because 1 over 2 times root x, that in fact goes to infinity as x goes to 0. Okay, so we can use this now to compute a concrete tangent line at x equals 1. Well, you need the slope and you need a point. Well, f prime of 1 is 1 over 2 times root 1, which is 1/2. F of 1, the y value, is square root of 1, which is 1. And now we remember that y equals mx plus b. Okay, there is the point-slope formula of the equation of a line, but y equals mx plus b, and a little bit of algebra, it just works out fine. We know that the slope is 1/2, so the equation has to be y equals 1/2 x plus b. And now we just plug in y and x. They're both 1 because the function goes through the point 1, 1. So we get 1 equals 1/2 plus b, and then b is 1/2 too. and the slope will be, or the equation of the tangent line then will be y equals 1/2 x plus 1/2, and we can certainly double check that. We plot the square root function, and we plot the line that we expect to be the tangent line at 1, and we can see from the picture, yeah, we should have gotten it right here. Now, with this formula, we can certainly compute a bunch of other tangent lines, also namely tangent lines at any point x, and I'm just showing a couple here. Remember, the slope is 1 over 2 times root x, and as x gets closer to the origin, we get steeper and steeper and steeper and even steeper tangent lines, and so at x equals 0, we'd also like to define a tangent line, but the problem there is that the derivative is undefined. However, what can be done is we can say the following. If you've got a function that is defined at a point a, and if f prime of x is the function that assigns to each x the derivative of f at x, and if one of the one-sided limits of f prime is infinite, then we will say that f has a vertical tangent line at a. Well, of course, if one of them is plus infinity, one of them is minus infinity, you could also talk about a cusp, but that's just basically a matter of an author's or a presenter's choice. When you've got an infinite tangent line or when you've got a cusp, something went wrong with differentiability, and well, you can classify that either way, at least for all that I'm interested in for this presentation. Okay, now velocities were also something that we dealt with, and so we're going to revisit this problem of finding the instantaneous velocity of a coin that was dropped off a 20-meter tall building, and we're going to find that instantaneous velocity this time at an arbitrary time t, not just at time t equals 1 or 2 that we had in the previous presentation. Okay, so the velocity is the limit as h goes to 0, position at t plus h minus position at t divided by h. We plug that in. We get negative 4.9 t plus h squared plus 20. That's s of t plus h minus negative 4.9 t squared plus 20. It's always helpful to put this stuff here in parentheses because, after all, we must not lose this negative sign up front here. And now, well, again, the 20 minus 20 goes away. And other than, yeah, okay, we just first multiply out parentheses. T plus h squared is t squared plus 2th plus h squared, and if we multiply that with negative 4.9, we get negative 4.9 t squared minus 9.8 th minus 4.9 h squared plus 20 is still copied down, and we're just pushing the negative sign through here. Minus 4.9 t squared is plus 4.9 t squared, minus 20 is copied down here, and here's the h. Okay, now the 20s cancel, the 4.9 t squareds cancel, and we're ending up with the limit as h goes to 0, negative 9.8 th minus 4.9 h squared. Remember, better safe than sorry, factor out the h and then cancel it. This is the limit as h goes to 0, negative 9.8 t minus 4.9 h. Note that the t doesn't depend on h, so that stays with us, and the limit is negative 9.8 t. Okay, well, that's good. That's the instantaneous velocity at an arbitrary time t, and it's measured in meters per second, of course. And well, if we have the velocity function of an object, and we do have that in the preceding example, then we can define the instantaneous acceleration of the object, and that is the derivative of the velocity at time t0. Okay, so symbolically, the acceleration is the derivative of the velocity with respect to time. And that means we can also, for this coin example, and I think that's what we're closing out with in this presentation, we can find the instantaneous acceleration, not just the velocity. And in order to do that, we take the acceleration, and that's the limit of v of t plus h minus v of t divided by h. We plug that into the velocity function, which is a pretty simple function, right? Negative 9.8 t plus h minus negative 9.8 t. Work out all the parentheses and the negative sign. We end up with a limit as h goes to 0, negative 9.8 t minus 9.8 h from here. Minus minus is plus 9.8 t divided by h. The negative 9.8 t plus the 9.8 t goes away. So we end up with the limit as h goes to 0 of negative 9.8 h divided by h. And that's negative 9.8. And that's measured in meters per second squared. Well, that's, of course, a strange looking unit, but remember, you can simplify units, and what that unit of acceleration actually is meters per second per second. So no, there's also no way to square a second, at least no way that I would consider explainable in elementary terms. Who knows, maybe quantum physicists have an explanation for something like that, but it's here just meters per second per second. Now, these computations with the difference quotients will stay with us throughout our work in this module on the definition of the derivative and its consequences. That can be a bit tedious, that is true, I admit that, but remember, it's just algebra. It's something we just do, and we want to have the capability to just do this kind of stuff routinely, and as soon as we have that, if we don't have it already, deeper work will become a lot easier for us than it would be otherwise if we had to worry too much about computations. Remember, computations, we have to get them right, but we don't want them to be a difficulty in principle, and the way around that is to practice. I'll see you next time.